Hello and welcome to 10.1 Notes. Today we're going to cover properties of a tangent to a circle. Okay, a tangent to a circle. So first let's review a circle. So a circle is the set of all points in a plane that are equidistant from a given point called the center of the circle. I really love that definition. I think that's really clever. I think we all know what a circle is. We're pretty familiar with a circle, but this is a neat mathematical definition of a circle. It's the set of all points, okay, in a plane. So it's a set of all points, like on a sheet of paper, that are equally distant from the center of the circle, okay? And the radius of a circle is the line segment that connects the center of a circle to any point on the circle. So here you have a circle, and you can see why it's the set of all points. Hold on here. The set of all points in a plane. A plane is like this piece of paper. It's the plane of this paper, and it's the set of all points that are equally distant. For example, if that's 12 inches, 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 that's 12 inches. And so it's all the points in a plane that are equally distant from that point. And that's the definition of a circle. Okay? And then a radius is the line segment that connects the center of the circle to any point. Okay? And remember, it's half the diameter. Okay? The diameter would be all the way across, right? Well, the radius is half that. It's from the center to the edge of the circle. And then we also have a chord. And a chord is a segment whose endpoints are on the circle. Okay, so you might want to write that down, that a chord is a segment whose endpoints are on a circle. Okay? And then we have the diameter. A diameter is a chord that contains the center of the circle. Okay? Okay, so you can copy these notes down, and remember, you can always pause this presentation, rewind it. You can go at your own pace. You're in total control of this presentation. But I just wanted to go over this again. Remember, a chord right here is a line segment. Okay, so it has a beginning and an end. A line goes on forever and ever and ever in both directions, but a line segment has a beginning and an end on this sheet of paper. And if its endpoints are on the circle, like that, that's a chord. Okay? And then here would be an example of another chord, right? Touching from there to there. Or, let's see, here would be another chord, touching from there to there. And a diameter is also a chord, but it goes through the center of the circle. So if it goes through the center of the circle, it's a chord, but it's a specific kind of chord. It's a diameter. And the diameter is the longest chord in the circle, correct? Okay, so moving right along, we have a secant. A secant is a line, so it goes on forever and ever and ever in both directions, that intersects a circle in 2 points. So here's an example of a secant. And then finally we have a tangent. A tangent is a line in a plane, in the plane of a circle rather, so it's in the same plane as the circle, like on the same sheet of paper of the circle, that intersects the circle in exactly 1 point. Tangent lines to a circle hit in exactly 1 point. That's very important. They touch the circle in exactly 1 point and 1 point only. And that 1 point is called the point of tangency. Okay, you can write that down and get caught up. I will continue, however. All right, in a plane, a line is tangent to a circle if and only if the line is perpendicular to a radius of the circle at its endpoint on the circle. So please write that down, get caught up. You can pause this if I'm going a little bit too quickly. But again, in a plane, a line is tangent to a circle if and only if the line is perpendicular to the radius of that circle at its endpoint on the circle. So what that means is, if you have line M, and line M, as in Mary, is tangent to circle Q, then that's true if and only if M is perpendicular to line segment QP. So if, and you know what I should do, I think, I should put the, should be line M, right? Oh, yeah, it is line M. Okay. So I have line M is perpendicular to line segment QP. So this would be your point of tangency, right? That would be your point of tangency. And if it is tangent at that point, then it is perpendicular to the radius. Okay? So what kind of problems could you possibly get based on this theorem? Well, here's one. Is line segment DE tangent to circle C? That's the question. Is line segment DE tangent to circle C? Well, remember, a line is tangent to a circle if and only if the line is perpendicular to the radius of the circle at the endpoint. In other words, only if this, only if this is a right angle. Okay? So if this whole thing right here is a right angle, then it's tangent. And if it is a right angle, I'd have a right triangle, right? And if I did have a right triangle, I can use the Pythagorean theorem. So basically, if the Pythagorean theorem holds true, and you get c squared equals a squared plus b squared, and it is in fact a right triangle, then obviously that means that the line is perpendicular to the radius, and therefore it is tangent. So that's how we're going to answer the question. Okay? So the answer is, if the Pythagorean theorem works and it's a right triangle, then yes, the line is tangent. Okay? And so let's fill in everything here. So it might look like we have this length, which is 3, and this length, which is 4, but it looks like we don't have the length of what might possibly be the hypotenuse, right, this longest leg. If this is a right angle, it would be, and if this was a right triangle, if CDE was a right triangle, then this would be the hypotenuse. And it looks like we don't know that length, correct? But look at that. Look at this figure for a moment. You can even pause this presentation and examine it. Do we know the length of CE? Well, yes, we do, because this is the radius. And remember, the radius is going to be, if the radius is 3, then that length is 3, and that length is 3, and that length is 3. These are all 3, and therefore that length is 3 as well. Aha. So that's sort of the clever little secret there. And you will have problems like that. Okay? So, moving right along, you get that you have 5 squared is equal to 3 squared plus 4 squared, right? Because we just went over that this is 3. So the whole length of this, line segment CE is 5. 3 plus 2. Right? Pretty clever. Okay. So if this is true, if the Pythagorean theorem works and 5 squared equals 3 squared plus 4 squared, then we do have a right triangle, therefore we have a right angle, therefore it's tangent. And you could even kind of stop right there too at this point. And if you remember your Pythagorean primitive triples, if this is a 3, then this whole length again is 5, and you have a 3, 4, 5, which does make a right triangle, right? So a 3, 4, 5 triangle is in fact a right triangle. But let's just assume you didn't notice that, or let's just complete the Pythagorean theorem. So we have 25 is equal to 9 plus 16, and yes, 25 is equal to 25. Therefore, yes, line segment DE is tangent to circle C. Okay? And then moving right along, this is another type of problem you can get based on this theorem. This one, conversely, tells you that ST is tangent to circle Q. It's saying, hey, it's tangent. Don't argue with it. It's tangent, and therefore this is a right angle. Okay? And it says then find the value of R. So again, we can use the Pythagorean theorem. C squared equals A squared plus B squared, and we have the C squared, the hypotenuse, even though it's not given. Okay, go back to that. even though it's not given, we know again if this is the radius r, this must be the radius r as well. So the whole thing is going to be r plus 18, right? This length qt, is r plus 18. So that's where we get the r plus 18 quantity squared from. It's this length qt, or the hypotenuse of this right triangle, right? And we do know it's a right triangle because it says it's tangent. So we have r plus 18 squared is equal to r squared plus 24 squared, right? And then you got to go back to your Algebra 1, people, and use FOIL, firsts, outsides, insides, lasts, and square that binomial and get r squared plus 36r plus 324. Okay, that's left side is based on taking r plus 18 and squaring it. And then on the right side we have r squared, which is right there, that r squared. And then 24 squared is 576. Okay? And then moving right along, fortunately we have r squareds on both sides, so those go away, making our problem much more easy to solve. And so we have that 36r is equal to 252, right? I just took 324 and subtracted 324 minus 324, you get 0. And 576 minus 324 over here gives me my 252. Okay, so we have 36r is equal to 252. Divide both sides by 36, and you get r is equal to 7. Okay, so we can find missing lengths that way. The radius of this circle is 7. Okay, and moving right along, we have another theorem here. Tangent segments from a common external point are congruent. Okay, please write that down. And here's the little diagram. So if line segment SR and line segment ST are tangent segments, then SR, or rather line segment SR, is congruent to line segment ST. So if RS is tangent to circle P, and if ST is tangent to circle P, then we know that SR is congruent with ST. Okay? The two are congruent. And what kind of problems can you get based on that theorem? Well, you can get problems like this. Find the value of x. And you have these points, they didn't say that they're tangent, but if they meet at right angles, right, the only way that they can be tangent is if they meet at right angles. So yes, these two line segments are tangent, and we need to find out what x is. Okay? So this is the exact same diagram. I just copied it and pasted, so we haven't missed a beat. You can just copy it from here. And then to solve, we just have, again, you need to know, the geometric principle that I'm testing here is you need to know that tangent segments that come from a common external point are congruent. So in other words, x squared equals 9. Okay? And then you take the square root of both sides, you get x is equal to root 9. The square root of 9 is plus or minus 3, but you can never have a negative distance, so x is equal to 3. Okay? So that's the end of the presentation. If you have any questions or concerns, please contact me at your convenience, and it would be my pleasure to help you. Okay? Bye-bye. And I just noticed that actually this value is x squared. So in this case, x can be negative 3. So the correct answer is x equals plus or minus 3. Because in this case, if x was negative 3, when you square it, you will get a positive 9. So it was my mistake earlier when I said that you cannot have a negative x. In this case, you can. Remember, you can't have negative distances, but this distance is x squared. So even if x was negative 3, when you square it, you get a positive 9. So in this case, like I just said earlier, x can be plus or minus 3. Okay? Bye-bye.